name is Nicolas Cadou, and it's a presentation about a game we are developing with Alice and Nick, and also 6 other developers. No, we are 6. So Blaise is also here, and 2 others are there. So I'm going to make an overview about the architecture, and then Nick will talk about API and game mechanics, and then Alice will show some good stuff. So what is Bachelor? So Bachelor is a TV show. It's a sort of a reality dating game. So a bunch of participants go in, and one by one gets eliminated, and one gets to be with the bachelor or the bachelorette. So we're making the Facebook version of it. All right, so this is the infrastructure. So there's a bunch of Python machines. Some of them are served by Nginx and USB. Some of them are not. They are doing some background stuff. They are all sharing a distributed cache, which is a Membase. Membase is based on Memcache, but it's also distributed and replicated, and optionally, you can have persistence. We run on top of a cluster of MongoDB servers, and all of this is behind a load balancer and a CDN. So this is a pyramid web app. We're using Mongo Engine, MAH00009, and a bunch of other stuff. We've taken a very layered approach, which is sort of looks like MVC. So the controller is served by pyramid routes and views, and the model is split between a core API and the data access layer, and of course the views are the views and the templates. So as I said, it's really layered. So for instance, in our views, there is very little game intelligence. It's mostly just translating what's coming from the web so that the API can consume it, the core API can consume it. The core API doesn't know anything about the web as much as possible. So, and also the API doesn't know a lot about the data store either. So we try to keep our views as thin as possible, so we avoid things like this one. And this is an actual view, which is not that bad, but it's using Tunable is a module where we keep all knobs so that BizDev people can make the game more addictive and get more money from users. And really, that doesn't belong in views. So yeah, the core API, we're trying to have it as much agnostic as possible. So it doesn't know anything about the underlying data store. So we encapsulate everything in object methods so that the code becomes much more easier to read than having the low-level stuff in it. And so we're using MongoDB. MongoDB, as you probably know, doesn't use SQL. In fact, it doesn't even have tables. So you can put whatever you want in it. So that's pretty cool, but also it can bite you. Mainly, it's very well suited to building clusters, and you don't have to do crazy stuff and lose the advantages of SQL in order to have distributed access to your data. And also, it's very hard to break. One of our co-developers, which is not here, has had a lot of fun trying to kill MongoDB. So we built a lot of configurations and then killed random processes, and all the time MongoDB just recovered. And he was sad because he likes to make in Python, there are not a lot of choices to use MongoDB. The two main contenders are MongoEngine and MongoKit. And because we felt a little bit limited with that, we decided to roll our own on top of PyMongo, and we ended up even more limited. So now we're switching to MongoEngine. And MongoEngine is really nice. So one might think that because you don't have any schema, that you have no need for migration, that you can just do it on the fly. But that's not entirely true, because even if the database is schemaless, you do want to have structure in your app, otherwise chaos will ensue. And a simple typo in the name of a field will go unnoticed, and you will have suddenly duplicated fields with weird names. So you do want to have the schema. You do want to have structure, and also for documentation, so that other developers can understand what you did. So this structure is going to need. Is going to have some changes in the lifetime of the app, and also data and content will change. So when a new feature gets deployed, it's very likely that some new data will be needed also. So it makes some sense that when you deploy the code, you have some scripts running and adding that content and maybe transforming the data. So yeah, with Mongo, we can do some migrations on the fly as soon as we access the object. But other than that, we use scripts, and also those scripts are going to be run automatically on deployment, so that nobody forgets anything. We also are using Lettuce as our testing framework. We also have unit tests, but for functional tests, Lettuce is pretty cool. So all tests are in feature files like this. So there is a description of the feature and then scenarios. And they are all in the same structure. It's based on a cucumber. I don't know if you know that. And it's always the same. Given something, when something happens, then this should be the result. And all of those lines are mapped to Python code. So, for instance, the third test, the third step in the scenario is mapped to that function using a decorator. It's auto-generated, that's why it's so long, because it's auto-generated. And the test only exercises the API, and that's it. So that's it.
Facebook and some game logic. Facebook integration is, well, Facebook by itself is a great thing for marketers. It lets you take advantage of existing accounts of users, their friends. The user can share. This is absolutely perfect for clients. It's not so fun for developers. This is actual code. What's the purpose of this? There's no ID when you ask to add the app, so it raises the exception before a user can register. The purpose of this check is to prevent the creation of a blank user when the Facebook API actually fails. So Facebook API constantly fails. There's a lot of problems for developers. There's These are only the most critical ones. Downtime. Caching doesn't always work. For a new user, you need to pull data from Facebook, and you don't want to break the experience if Facebook is down. Speed is also an issue. Every request also results in a round trip to Facebook, slowing every action on your script down even further. Some of this can be done asynchronously, but not everything is possible. Facebook has improved this lately with their Open Graph implementation, but it's still slow and it suffers from downtime. There are sudden changes to the API with no announcements. They do this all the time. I think they enjoy this. They like seeing developers using their API suddenly confused why their apps aren't working. They've been using the same API calls for a year, and all of a sudden their entire application doesn't work. Some new permission is required, or a permission has to be used differently. Some new variable is added that's required, and they don't announce these things always. This is also a problem with documentation. It's comparable to early stage free open source software. No complaints about open source software, but documentation for the projects isn't always that great, and Facebook is just like them. API isn't fully documented, examples aren't there for everything. Some features you can only find out about through forums or trial and error. That's not how an API should work. For example, one horrible example of this is errors. Errors will be returned as a list of one string, but a successful message will be returned as just a string. And they don't document this, you only have to find out yourself. So this is a useless complaint about Facebook, unless you happen to know Facebook developers you can complain to. But we can improve our own public APIs. Keep it simple. From the Zen of Python, namespaces are one honking great idea. Let's do more of those. Seriously, hierarchical organization is easy to understand and use. Your APIs should reflect your data and be organized that way. Document every API call. Explain what it does and any nuances. The name is not enough to figure out what a function does. New developers will need trial and error to guess your API, and that's not okay. Document every variable, just like the API calls. Specify the type, possible options, if it's required. Everything about your variables you need to explicitly state. So, onto game logic in Python. We had a giant flowchart like this. There's more after this, another about 2.5 times this, and we need to convert all these different steps and roles. There's contestants and friends of them, and the system has certain actions to do, and we need to convert this into Python objects. Hard coding it wasn't an option. So multiplayer social games are step and role based, which makes them suitable for finite state machines of a sort. With converting them to objects, there's consistent methods to show and get the next step in the game, or to limit the user so that they can't go to the next step unless another user takes an action. Ajax support and all sorts of options, getting the next URL. And security is also easy to implement. You can prevent a user from going to the next step because everything is an object. You can easily reference the next one, see if they're prevented from going to that step. This starts to lead into next discussion. Certain tasks in the game shouldn't be blocked by one user. If one user doesn't check their Facebook or something happens, they can't advance the game, they can't continue to play. The system has to take over. They have to force a move. And so there are system steps that will automatically come into play, and timers which can expire and cause automatic system actions. This is an example of the code we use to model steps with different roles and different actions throughout the game.
So I wrote a MongoDB-backed RPC system to allow these background timed tasks as well as some Facebook calls to run in the background. So yeah, we need it for game events and because Facebook API sucks. It executes things in the background either immediately as a current RPC system or scheduled at some point in the future. The possibility is also there for cron-like jobs. It captures responses and any exceptions that are generated within these background tasks. So we have a full log of everything that goes on, when and where. And it acts with, like a state machine, allowing us to, if a task, for example, can't get run within a certain period of time, we can rerun it on a different worker. The MongoDB backend for this is a standard collection for all of the job-related data, the arguments to it, any responses, etc. It also uses a capped collection for notification of workers and notification of completion. Futures, which is a core part of Python 3.2 and backported into the future package, allows us to run things in thread and process pools very, very easily. And AP Scheduler is used for the scheduled tasks. Atomic locking jobs getting grabbed by workers is done using update of current, which is a feature of MongoDB, which errors out gracefully if something is not the data we would expect. Capped collections, in case nobody here is aware, are limited size and optionally limited document count standard collections. They act as a ring buffer, so they get appended to and eventually they start getting appended to the beginning again. You can update, but there are some restrictions on that. For example, the record cannot increase in size. It's used by MongoDB internally for replication and sort of push notification to replication slaves that there's new data to roll. And uses tailable cursors, which are like IMAP idle, long hold. And live demonstration should be relatively quick. So, script here. You need to create some collections with this drop we've got. Create a collection of jobs. We're going to create a 512 megabyte capped collection. And I got some stuff in Python here, so pretend you didn't see that. Import a few things. We create an instance of our worker. The true is for master mode. We submit a print job. Now, no workers are running, but if you start one, you'll note there should be a print statement somewhere. There we go. Hello world. It keeps track in the collection of, in production, about 8 gigabytes worth of push notifications. So if a worker gets started up really, really late, it can catch up quite easily. If I start up 2 workers here, and submit, say, 1,000 jobs to them. And that was just running on one machine. In a cluster, the latency is actually sub-millisecond, as well as round-trip times, standard deviations around 0.00067 seconds. It's very, very efficient. And we can also submit timed tasks. So if we start 10 timed tasks over 2 seconds, you can see the workers fighting it out over which one's going to accept the job already accepted, etc. The job records look like this. So we have standard ID, state, which can either be new, pending, dead, canceled, running, or finished. Some of these states only apply to scheduled tasks. For example, you can't cancel an immediate task. The callable is a simple pickle, which offers some restrictions on what you can actually call in the background. You can't call instance methods, for example. Arguments and keyword arguments, we allow submission of tasks using either. Has a creation date and a creator. The creator is the host name, parent process ID, and child process ID, and this helps us keep track of things in logs. Owner is null or a similar sort of identity. If it's scheduled, only then do we actually have the when key. It's not there in the data at all if it's not scheduled. Acquired only exists once the job's been accepted by a worker, and the state generally is set to running. And if once it's completed, the result, exception, and completed piece of data are added as well. So if there's an exception, we actually get the trace back in the database. The actual notification records are very, very tiny. This allows us to, in about 8 gigabytes of data, we estimated about 1 million users over the course of a year would fill up that collection. It'll last us quite a while. Now there's a little bit of a quirk with MongoDB, the very first record there, is if the capped collection is empty, you try to do a tailable cursor on that cat collection, sorry for time, it will go into a busy loop, and your server will go to 9 load, terrible. So we insert a not record just in case. New jobs look like that, and finished jobs simply have an extra key. Python generators, that's how you run through a queue. Just a series of nested while loops to handle different error conditions. The while cursor alive, and the for loop there, the for loop actually blocks until additional data is available, but it times out every 10 seconds, so we need to wrap that in another while. And if it ever bombs out, we keep track of where we last were. And this is the handler that actually runs the jobs. It's been neutered a bit. And you can see the update. As long as the data has that ID, the state is pending, and there's no owner, we update it to say, we are the owner, we're running it, and this is our identity, and when it was fired. If that fails for any reason, someone else already grabbed it. The very bottom it actually executes that. So, yeah, that actually executes it. And there we go. Absolutely none.
Maybe we can talk about that.
There was one question.
Question. I came about to work on this project. I mean, Basher is something on TV, must be like a bunch of legal and so on, or license.
I guess to have that answer, you'll have to talk to the legal team over here.
Our boss is in the audience, so I'm not really sure how much we can say.
All right, is it deployed?
Not yet.
Okay. So it's made in Montreal.
Yes. Yep, back there.
So about your job queue, I've seen many places re-implement job queues in many variations. What was your motivation for rolling your own?
When we first started the project, rather when I first joined the project, was after development began. We had dependencies for ZeroMQ and RabbitMQ because we needed both low latency and persistence. And I had previous experience with MongoDB using it as a queue system, and it solves all those problems in one. It also replicates extremely easily. The query here says slave open is true, so it actually distributes really, really well. I pretty much already kept it.
On va passer la soirée au Benelux, juste à côté de la chance. Il y a une bière gratuite qui vient de Benelux, une autre qui vient de le site, et je vais avoir des tickets, vous allez juste à me suivre, vous rejoindre là-bas. Et le pouvoir est pas inclus.